China included in the 14th Five-Year Plan for Energy Technology Innovation. And now, the technology has achieved a milestone and is expected to show broader application prospects in many more fields.
A few weeks ago, China flipped a switch on a machine that most engineers thought was still a decade away from being real. Not a prototype sitting in a lab, not a concept on a whiteboard, an actual working power generator connected to a real electrical grid, pumping out power for a real steel factory. And the numbers coming out of it are honestly hard to believe. The same amount of heat that used to produce a certain amount of electricity is now producing 50% more. The machine doing it is half the size of what it replaced. And the whole system is running on something you breathe out every single time you exhale: carbon dioxide. Now, before you laugh that off, stay with me. Because what China just turned on is not a tweak to existing technology. It is a fundamentally different way of converting heat into electricity. One that scientists and engineers have been dreaming about for over 60 years. And the reason it matters so much is that the thing it is replacing, the steam turbine, has been sitting at the heart of almost every power plant on Earth for over 140 years. We are talking about potentially ending the steam age. And it just quietly happened in a steel plant. If this kind of content is something you find valuable, a like on this video genuinely helps other people find it too. Now, let us talk about what this machine actually is, why it works so much better, and most importantly, why this announcement is both genuinely exciting and also worth looking at a little more carefully. The engine that runs the world and why it is kind of embarrassing. Here is something wild to think about. Right now, whether your electricity comes from coal, gas, nuclear, or even some solar thermal setups, the final step in turning heat into electricity is almost always the same. You boil water, you make steam. The steam pushes through a turbine. The turbine spins a generator. That is it. That is the big secret behind the modern power grid. Boiling water. The basic idea behind this has not changed since the 1800s. We have gotten much better at it over time. Modern steam plants are engineered to incredibly precise tolerances. The materials are exotic. The pressures are extreme. The temperatures inside the best modern steam turbines would melt most metals you would find in everyday life. But the core concept, heat water, make steam, spin a turbine, is still Victorian. It is essentially the same logic that powered the factories of the Industrial Revolution, just done with far better tools. And here is the embarrassing part. Even the best steam turbines in the world today only convert about 35% of the heat they receive into actual electricity. The rest, roughly 65%, just gets thrown away as waste heat into the air or into a nearby river. More than half the energy in every fuel we burn just disappears before it ever reaches your light switch or your phone charger. Think about what that means in practice. Every coal plant, every gas plant, every nuclear plant is essentially a very expensive machine for throwing away energy. We accept this because it has always been this way. But engineers have known this is a problem for a very long time, and they have been searching for something better, something denser, something more efficient. Something that does not waste 2/3 of the energy we put in. The answer they kept coming back to was not a better steam turbine. It was a completely different fluid altogether. And to understand why that fluid is CO₂ of all things, you first need to understand one of the strangest and least talked about facts in all of physics. The strange state of matter nobody talks about. Every substance you know, water, air, metal, has 3 basic states: solid, liquid, gas. You learned this in school. But there is actually a 4th state that most people never hear about, and it only happens under very specific conditions of temperature and pressure. Push the temperature and pressure of almost any substance high enough, past a certain threshold called the critical point, and something strange happens. The liquid and the gas stop being different things. They merge into one. The substance becomes what scientists call a supercritical fluid. Think of it like this. Normally, a liquid and a gas are like two completely different people. One is dense and heavy, the other is light and airy. They behave differently, they look different, and they do completely different jobs. But in the supercritical state, they become the same person, dense and heavy like a liquid, but flowing freely and easily like a gas. It is a genuinely weird thing to wrap your head around, but it is completely real, and it has been understood since the early 1800s. Now, here is where CO₂ becomes extraordinary. For water, reaching that critical point requires a temperature of 374 degrees Celsius and a pressure of about 220 atmospheres. That is brutal. That is the kind of extreme environment that chews through materials and makes engineering incredibly expensive and difficult. But CO₂ reaches its critical point at just 31 degrees Celsius and about 70 atmospheres. 31 degrees. That is basically a warm afternoon. The pressure requirement is also far more manageable than water. By comparison to what supercritical water demands, supercritical CO₂ is almost embarrassingly easy to achieve. And once you push CO₂ past that point, something remarkable happens. It becomes incredibly dense, nearly as dense as liquid water, but it still flows through pipes and turbines as easily as a gas. That combination is almost tailor-made for generating electricity. Here is why that density matters so much. In any turbine, the more mass you can push through the blades per second, the more power you extract. Steam is not very dense. You need an enormous machine to push enough of it through to generate serious power. The turbine halls in major power plants are the size of aircraft hangars because of this. But supercritical CO₂ is dense enough that you can push a huge amount of mass through a much smaller machine. The turbine blades are smaller, the pipes are smaller, the whole power block shrinks dramatically. And because of how the thermodynamics work in this kind of cycle, far less energy gets thrown away along the way. The theoretical efficiency for supercritical CO₂ systems runs between 45 and 50%. Compare that to the 35% ceiling of the best steam plants, and you start to understand why engineers have been genuinely excited about this for decades. But there is a very large gap between understanding why something should work and actually building it without it destroying itself. That gap turned out to be one of the hardest engineering puzzles of the last half-century. Why nobody has done this before? If supercritical CO₂ is so much better, why has it taken until now to actually build one? The honest answer is that building one is genuinely brutal in ways that are easy to underestimate from the outside. The first problem is heat and chemistry together. To get the best efficiency out of a supercritical CO₂ system, you need to heat the CO₂ up to around 700 degrees Celsius before it hits the turbine. At those temperatures, most metals begin to slowly stretch and deform under sustained pressure in a process called creep. Imagine a metal bolt that very slowly gets longer over years just from the heat and the load on it. That is creep. In a power turbine, it is a serious problem because even tiny deformations in the wrong place can cause catastrophic failures. But the CO₂ itself makes things worse. At high temperatures and pressures, CO₂ starts to force carbon atoms into the grain structure of certain metal alloys. Over time, this makes the metal brittle. A turbine blade that becomes brittle while spinning at tens of thousands of rotations per minute inside a system at extreme pressure is not a small inconvenience. It is a potentially catastrophic failure. So engineers need special alloys, exotic metals carefully designed at a microscopic level to resist both the heat and the chemical attack from the CO₂. These alloys exist, and they work reasonably well, but they cost many times more than regular steel. And because nobody has actually run these machines for 20 or 30 years in real-world conditions yet, Nobody knows with complete certainty how they will behave over a full plant lifetime. That uncertainty makes investors and plant operators very nervous. The second major problem is the heat recycler, and this one is arguably even more difficult. One of the key reasons supercritical CO₂ systems are so efficient is that they capture the heat from their own exhaust and feed it back into the incoming fluid before it even reaches the main heat source. This recycling step is responsible for a huge chunk of the efficiency advantage. But to make it work at the level required, you need to transfer an enormous amount of heat across an incredibly thin wall, while keeping both sides at pressures approaching 200 atmospheres. The engineering tolerances involved are almost absurd. The hardware built to do this job looks like nothing else in power engineering. Engineers chemically etch tiny channels, some narrower than a human hair, into flat metal plates, then fuse thousands of those plates together into a single solid block containing millions of microscopic flow paths. The result is a device that is extremely compact, extremely strong, and extremely efficient at transferring heat. It is also nearly impossible to inspect once it is assembled, impossible to take apart for repairs, and extraordinarily expensive to manufacture in the first place. If a crack develops anywhere inside that block while it is sitting at 200 atmospheres, the results are severe. The third problem is the turbine speed itself. Because the CO₂ is so dense, the turbine can be physically small. But small turbines need to spin very fast to extract the same power, often tens of thousands of rotations per minute. At those speeds, regular bearings with oil lubrication would generate so much heat from friction that they would fail within hours. So engineers have had to develop alternatives. Some teams have built magnetic bearings that hold the spinning shaft in place using magnetic fields with no physical contact at all. Others are experimenting with bearings that float on a thin cushion of the CO₂ itself. Both approaches work in controlled settings, but both are also complex, expensive, and have not yet been proven over decades of continuous industrial use in demanding environments. All of these challenges together explain why, despite 60+ years of research, dozens of test programs, and enormous amounts of money spent across multiple countries, nobody managed to get a supercritical CO₂ system onto a real commercial power grid until December of 2024. That is when China changed the story entirely. Here is my question for the comments. If supercritical CO₂ turbines become the new global standard, which industry do you think benefits the most? Nuclear, steel, shipping, or something else entirely? Let me know what you think below.